Today we will discuss an energy distribution whose form we currently know very little about, but which sculpted the very earliest moments of our universe and allows for our very existence. An energy distribution whose mapping is a key, no-lose deliverable of any larger, more powerful particle collider. Today we will discuss the Higgs potential.
The point about darkness is you float in it. You and the darkness are distinct from each other because darkness is an absence of something. It's a vacuum. But total light envelops you. It becomes you. It's very strange. I recommend it.
According to quantum field theory, the vacuum of our universe is not empty, but rather a boiling sea of quantum fields. These fields have associated energy potentials, distributions that control the average values the fields take in the vacuum of our universe. Fortunately for us, one of those potentials, the Higgs potential, is not like all the others. In episode 1 of this series, we learned why exquisite measurements of the Higgs boson and related physics, measurements which require and demand new colliders, are so incredibly important. Today, in episode 2, I will introduce a key pillar of the Higgs physics program at future high-energy colliders: understanding, measuring, and mapping the Higgs potential. Today I will explain what the Higgs potential is, and outline the form it takes within the framework of the Standard Model, explain the problems it addresses and solves in particle physics, and break down the concept of electroweak symmetry breaking, the process that imbued fundamental particles with their mass, and the process that allows us to be here to ask any questions at all. I will also explain how the true Higgs potential of our universe remains a deep mystery. This will bring us to the realization that despite the discovery of the Higgs boson at the Large Hadron Collider, our understanding of how fundamental particles obtained their mass is still woefully incomplete. This knowledge will allow us to explore, in episode 3, why measuring the true form of the Higgs potential in our universe at new, more powerful particle colliders is so uniquely important, and may finally allow us to answer some of the most fundamental questions humanity has wrestled with for millennia. So let's get to it. What is the Higgs potential? Potentials are energy distributions plotted as a function of some variable or variables. Take the Lennard-Jones potential, which models the potential energy of a two-atom system as the separation distance between the atoms varies. Physical systems tend to sit at the minima of such energy distributions. Balls roll down hills, springs snap back after they've been stretched, water comes to rest in a depression, and chemical bonds form at separations which minimize the potential energy of a system. Quantum field theory tells us that the vacuum of the universe isn't really empty, but in reality is a boiling sea of quantum fields associated with every fundamental particle we know and do not yet know. All of these fields have an associated potential, which depends on the strength of the field in the vacuum. Usually the potential energy distribution of quantum fields takes a parabolic shape, and these fields, although oscillating, take an average value of 0, the value of the field that minimizes the potential energy. We can excite fundamental particles out of the fields by pumping energy into them, like we do at particle colliders, but on average, these quantum fields are turned off. However, this is not the case for the Higgs field. In the Standard Model of particle physics, the Higgs field is the key to providing mass to the W and Z bosons that mediate the weak nuclear force. The Higgs field also acts as an omnipresent treacle that exists everywhere in our universe. Fundamental fermions like quarks and electrons ping off that field and also obtain their mass. Evidently, the Higgs field is dialed up to a non-zero field strength everywhere in our modern universe. The Higgs field is constantly switched on everywhere. This makes the Higgs field a black swan amongst quantum fields. The Higgs potential is the Higgs field's vacuum energy density, the energy density stored in the omnipresent Higgs field, the Higgs field's contribution to the energy density of empty space. Evidently, given that the Higgs field is constantly dialed up everywhere, that potential is not parabolic about the origin, but instead displays a minimum at a specific, non-zero Higgs field strength, the Higgs vacuum expectation value. This is the minimum at which the vacuum of our universe sits. This Higgs potential is dependent on the strength of the Higgs field in the vacuum of our universe. If the strength of the Higgs field were dialed up, the energy density of empty space would increase. The same would happen if the Higgs field were gradually switched off. But how can this be the case? How can having a quantum field constantly cranked up create a minimum in the energy density of the vacuum overall? How can the Higgs behave differently to all other quantum fields? Well, according to the Standard Model, the form of the Higgs potential has evolved as our universe has evolved. In the very earliest moments of our universe, the Higgs potential took a parabolic form similar to other quantum fields. The Higgs field was powered off. Fundamental particles were massless and whizzed around the universe at the speed of light. However, after around 10 to the minus 11 seconds, the universe underwent a phase transition, the electroweak phase transition, and the Higgs potential morphed from a parabolic shape into its current shape, the infamous Mexican hat or wine bottle classical Higgs potential. The vacuum of our universe then rolled down the classical Higgs potential energy hill into its current low energy state. The Higgs field was powered on to its vacuum expectation value, and the weak gauge bosons and fundamental fermions acquired their mass. As such, the changing form of the Higgs potential outlined by the Standard Model helps us to resolve the riddles of weak gauge boson and fermion masses, and is vital to understanding the evolution, current state, and potential future of our universe. The discovery of the Higgs boson in 2012 was the smoking gun that gave away the existence of the Higgs quantum field. And since 2012, particle physicists have verified that the Higgs boson conforms to our theoretical predictions. So you might very reasonably think that the Standard Model Higgs mechanism is the complete explanation for how the weak gauge bosons and fundamental fermions, neglecting neutrinos, acquire their mass. We're done here. However, that is not the case. The Standard Model provides our current best guess as to how the Higgs potential has evolved since the dawn of our universe. However, it may surprise you to learn that despite the ubiquity of the Standard Model classical Higgs potential in modern physics media, the true Higgs potential of our universe and its evolution have never been experimentally verified. Despite the discovery of the Higgs boson in 2012 and more than a decade of subsequent study, we have minimal knowledge of how the vacuum of our universe arrived at its current state, and the past and current forms of the Higgs potential. The classical Standard Model Higgs potential is the simplest potential that results in a universe where the weak gauge bosons and fundamental fermions have mass. It is the simplest form of the Higgs potential that gets the job done. It is a theorist's first estimate. That doesn't mean it's the true Higgs potential of our universe. There are many ways that the vacuum of our universe could have rolled down the Higgs potential hill and left us with the universe we observe today. All of these potentials are linked with a radically different evolution of our universe. In the following sections, I will explain the evolving form that the Higgs potential takes in the Standard Model, the historical and physics-based motivations behind that form, and the deep problems that that form solves in particle physics. It is a fascinating story. We will then explore how that classical Standard Model form of the Higgs potential may not be the true form of the Higgs potential in our universe, and how our journey towards understanding electroweak symmetry breaking and how fundamental particles acquire their mass has only just begun. To understand how theoretical physicists arrived at the form of the classical Standard Model Higgs potential, how it's linked to a phase transition in the very vacuum of our universe, and how that potential helps to solve the riddles of particle mass, we need to dive into the physics of phase transitions and the work of Lev Davidovich Landau. In the middle of the 20th century, Landau theory proved to be incredibly successful in describing a broad range of phase transitions, including the Landau-Ginzburg theory of superconductivity. Consider a simple toy system, a 2D system of atoms arranged in a plane. Each atom has a magnetic moment that can point either up or down. At high temperatures, above the phase transition or critical temperature, the atoms flip between pointing up or down due to their thermal motion. The system is disordered, but on average there are equal numbers of magnetic moments pointing up and pointing down, and the system has zero net magnetization. However, when the system is cooled below the critical temperature, the atoms align magnetic moments to minimize the overall potential energy of the system. The system becomes more ordered and develops a net magnetization in a particular direction, up or down. The magnetization is the order parameter. It increases from 0 to a finite value. Notice that this simple system can produce a net magnetization in the up or down directions with equal probability, as both choices align the magnetic moments and lower the potential energy of the system by the same amount. We say that the potential energy of the system is symmetric with respect to up to down rotations. In Landau theory, the potential energy of the system in the vicinity of the critical temperature is given by the following equation: alpha magnetization squared plus beta magnetization to the power 4. Notice that only even powers of the magnetization are permitted, as otherwise the potential energy of the system will be dependent on whether the magnetization pointed in the positive up or negative down direction. In theory, higher order terms in magnetization to the power 6 and magnetization to the power 8 are also permitted. The beta coefficient in the potential energy equation is always positive. However, the alpha coefficient switches its sign depending on the temperature. Above the critical temperature, alpha is positive, and the potential energy shows a single minimum at zero magnetization, where the system naturally sits. Alpha decreases as we approach the critical temperature. At the critical temperature, it becomes 0, and the potential has a wide, flat bottom, still centered around zero magnetization. However, below the critical temperature, alpha flips sign and becomes negative, and the system develops two identically deep minima, one corresponding to all magnetic moments pointing up, and the other corresponding to all magnetic moments pointing down. We can find the position of the minima with simple differentiation, plus or minus the square root of minus alpha over 2 beta. Below the critical temperature, the system spontaneously falls into one of these two minima. Switching on a directional magnetization now leads to the system sitting lower in energy than not doing so and maintaining an overall magnetization of 0. Notice that there is an important difference in symmetry between the high temperature and low temperature phases. In the high temperature phase, the potential energy of the system and the magnetization of the system, on average 0, were symmetric with respect to up to down rotations of the magnetic moments, and hence swapping m to minus m, 0 equals 0. If I swap all the ups to downs and all the downs to ups, nothing changes. However, in the low temperature phase below the critical temperature, the rotational symmetry of the magnetization is lost. Swapping the magnetic moments from up to down changes the sign or direction of the magnetization, but crucially, the potential energy of the system remains symmetric and invariant under such rotations. Notice that the loss of symmetry in the final state is accompanied by a gain in order of the system, as measured by the order parameter, the overall magnetization of the system. This kind of symmetry breaking, where the energy given by the underlying interactions in the system is symmetric, but the ground states of identical minimum energy are not, is known as spontaneous symmetry breaking. The underlying physics between magnetic moments is completely symmetric and ambivalent with respect to up to down rotations, but that fact is hidden by the observation that all the magnetic moments are pointing up or down after the phase transition to the low temperature phase occurs. When we only observe the final state of the low temperature phase, we are tricked into believing that the underlying physics of magnetic moments is not symmetric with respect to up to down rotations, that there is some underlying preference for magnetic moments to all point up rather than down. However, that is not the case. The underlying symmetries of the fundamental magnetic physics are completely intact. It just so happens that the system fell into the ground state with all magnetic moments pointing up. Another example of spontaneous symmetry breaking is a ball sitting on the apex of a smooth hill. When it rolls down the hill to a lower energy final state, it could choose to roll down along any path, but it has to choose one. There is no preferred direction dictated by the physics of gravity, But when we observe the ball sitting to the east of the hill, we might believe that gravity favours falling to the east. But it does not. If we let the ball roll down dozens of times, it might choose different paths each time. Again, the underlying symmetries of the fundamental gravitational physics are completely intact. They are just not manifest in the final, specific ground state of the system. It turns out that such spontaneous symmetry breaking is the key to understanding the origin of particle masses within the Standard Model. So, we now understand a very simple ferromagnetic phase transition, but how does that relate to the Higgs potential? Well, we can use a very similar framework to hypothesize that a phase transition occurred in the very vacuum of our universe. Notice how the spontaneous switching on of a non-zero magnetization throughout our toy ferromagnetic system closely mirrors the powering up of the Higgs field to a non-zero vacuum expectation value throughout the universe. Perhaps the universal vacuum itself underwent a phase transition that switched on the scalar Higgs field everywhere in our universe. And it turns out that this idea solves a multitude of problems in high-energy particle physics. By the 1960s, quantum field theory had already successfully described the physics of electromagnetic interactions. However, applying quantum field theory to the weak interaction, which controls radioactive decay, was proving impossible due to a fundamental stumbling block. The theory didn't allow for particles to have mass. If the bosons are not massless, the fundamental underlying gauge symmetries of the theory are broken, and the theory collapses mathematically. Electroweak theory, where the weak force and electromagnetic force are unified, predicts that 4 massless bosons should control electromagnetic and weak processes. We call them the W1, W2, W3, and B. This posed a major problem in the 1960s, since it was clear that the weak force carriers had to be massive to be consistent with their very short range, and the slower pace of weak interactions and radioactive decay that scientists observed. Scientists needed a workaround to explain how it could look like the weak bosons we know today, the massive W+, W-, and Z, appear to break the underlying gauge symmetries of electroweak theory, but in reality, do not. They needed a mechanism that explained how electroweak fields could obey the underlying symmetries of gauge field theories that demanded that all gauge bosons should be massless, but the final vacuum state of our universe does not. The parallels to Landau's theories of phase transitions and its associated spontaneous symmetry breaking were undeniable, and Peter Higgs and his contemporaries sought to introduce Landau's ideas into particle physics in the 1960s. Peter Higgs demonstrated that a symmetry like that underlying electromagnetic interactions, the U1 symmetry, could be spontaneously broken if one assumes the existence of a special field which uniformly fills the entire universe and is non-zero on average, even in completely empty space. This model was just an illustration, since the electromagnetic symmetry is in fact not broken, but it proved to be a breakthrough idea. Steven Weinberg and Abdus Salam used Higgs's ideas to show that the weak symmetry is spontaneously broken. Weak interactions respect the underlying symmetries of gauge field theories, but the state of minimum energy, the vacuum of the universe, does not. W and Z boson masses only appear to violate the electroweak symmetry, just as the ferromagnet in the low temperature state appears to violate the up to down reflection symmetry. It turned out that the key to solving both the problem of the masses of the W and Z bosons and the non-zero value of the scalar Higgs field throughout the universe is the same. A new field present from the very beginning of our universe, the primordial Higgs field, and Landau's sleight of hand, spontaneous symmetry breaking. What Higgs and several other brilliant 1960s theoretical physicists proposed was that just like our simple ferromagnetic system, the very vacuum of our universe had undergone a phase transition in its very first nanoseconds, the electroweak phase transition. This phase transition gave mass to the W and Z bosons and powered up the scalar Higgs field that pervades the universe today, imbuing mass to fundamental fermions. Here's how it works. Physicists hypothesized that the Higgs field existed in the very earliest moments of our universe, but at that point it had 4 components. It was a field that specified 4 values at different points in space, just as we can specify the temperature, humidity, pollen count, and air density at different positions in a room. It had 4 degrees of freedom. These 4 degrees of freedom can be expressed as 2 complex fields with 4 components. Higgs also postulated that the potential energy of this field took the following form: mu squared phi dagger phi plus lambda phi dagger phi all squared. Mu squared is the mass squared term, while lambda is related to the Higgs self-coupling strength, something we will discuss in later episodes. Notice how this potential energy looks exactly like the potential energy in the Landau theory of the ferromagnet, just with the order parameter of magnetization switched to being the strength of the Higgs field. That is no coincidence. Higgs and others lifted the form of the potential straight from Landau's work. Notice also that just like the potential energy of the ferromagnet was invariant under up to down rotations, the potential energy associated with the Higgs field is symmetrical to rotations in phi space. Swapping all the phi components around leaves the potential energy of the system unchanged. At extremely high temperatures in the very early universe, above a critical temperature, the mass squared term was positive, just as the alpha term in our ferromagnetic system was positive, and all 4 components of the Higgs field had an average value of 0, just as our toy ferromagnet had an average magnetization of 0. In the earliest moments of the universe, the vacuum was at the origin, with all the Higgs field components taking an average value of 0. Rotations of the 4 components of the field did nothing to the physical state of the system, just like swapping up to down did nothing to the magnetization of our ferromagnet. Symmetry was maintained, and there was no constantly turned on Higgs field for fundamental particles to bounce off and acquire mass. Particles were massless and whizzed around at the speed of light. However, as the universe cooled, its temperature dropped below a critical temperature, and the vacuum underwent a phase transition. Just as for the ferromagnet, our mass squared term turned negative. The electroweak phase transition occurred. Just like the ferromagnetic system, the potential energy continued to be symmetric to rotations in phi space, but a ring of degenerate final state energy minima developed. The position of that ring of minimum energy states can be found by again taking a simple derivative and setting it equal to 0. The 4 field component squared terms have to sum to minus mu over lambda. This is hard to visualize in 4D space, but it creates a ring of identical lowest energy vacuum ground states in complex space, the famous Higgs wine bottle potential. The early vacuum of our universe was now free to roll down the Higgs energy potential hill and into any of those final state minima, and it did so. This is just like our ball rolling east down the hill. However, when the vacuum rolled into the specific minimum, it chose a particular component, a specific direction, and it spontaneously broke 3 directions of the Higgs field. If we now rotate the system, we turn on different components of the Higgs field. Rotations change the physical nature of the system. The system is no longer symmetric under phi rotations, rotations of the Higgs field components. Just as in our ferromagnetic system, the magnetization switched from M to minus M as we rotated up into down. The symmetry of the Higgs field has been spontaneously broken. The result is that we now have a Higgs field component turned on throughout the entire universe, a scalar field which fermions can bash off to acquire their mass. But there's more. There is a famous theory in particle physics, known as Goldstone's theorem, that states that when a continuous symmetry exists and is spontaneously broken, like the vacuum choosing one ground state from a continuous ring of ground states, integer spin particles, bosons, will be generated. These Goldstone bosons are massless and generated in numbers that correspond to the number of degrees of broken symmetry. So in this case, the spontaneous symmetry breaking of 3 directions or components of the Higgs field generates 3 massless Goldstone bosons. And here's where the magic happens. These Goldstone bosons have the same quantum numbers as 3 of the 4 massless electroweak gauge bosons, the W1, W2, W3, and B, so they can mix. Notice that the Higgs field had 4 degrees of freedom before spontaneous symmetry breaking, and that massless gauge bosons like the W1, W2, W3 and B have 2 each, just like a photon has 2 transverse polarizations. That's a total of 12 degrees of symmetry before the spontaneous symmetry breaking of the Higgs field. Now, when the electroweak gauge bosons and the Goldstone bosons from the spontaneous symmetry breaking of the Higgs field mix together, the degrees of freedom are repackaged into the force-carrying bosons we know today, the massless photon and the massive weak W+, W-, and Z bosons. So after the process of electroweak symmetry breaking, we have the massive W+, W-, and Z bosons with 3 degrees of freedom each, 2 transverse and 1 longitudinal, the massless photon with 2 degrees of freedom, and 1 degree of freedom left over, a new scalar particle, the massive Higgs boson. 12 degrees of freedom before the spontaneous symmetry breaking of the Higgs field, 12 degrees of freedom after. By the end of the electroweak phase transition, the W and Z bosons have mass, and at no point were the W1, W2, W3 and B gauge bosons required to have mass and break their underlying gauge symmetries. The spontaneous symmetry breaking of the Higgs field did all the work, imbued them with mass, and just left us with the final state of the universe where it looks like the gauge symmetry was broken. In reality, as with our ferromagnetic system, or with a ball rolling down a hill, the underlying symmetries of the fundamental physics are completely intact. This is the process of electroweak symmetry breaking. This process also left us with an omnipresent Higgs field switched on everywhere in the universe, a field off which fundamental fermions can ping to obtain their mass. Peter Higgs and his contemporaries had applied Landau's theory of phase transitions in ferromagnets to the very vacuum of our entire universe, and found a loophole to provide fundamental particles with mass without breaking the symmetries essential to gauge field theory. This was an incredibly beautiful, if diabolically subtle, theoretical breakthrough. Don't worry if you have to listen to this section a couple of times to get a handle on it. The important point to take away from this section is that the form of the Higgs field and Higgs potential was chosen by Higgs in such a way that a phase transition in the very early universe could provide just the right amount of spontaneous symmetry breaking to produce the 3 massive weak gauge bosons we see today, and to switch on a scalar field throughout the universe that explains how fundamental fermions acquire mass. The forms of the Higgs field and the Higgs potential were chosen to get the jobs done. Putting this Higgs mechanism together with electroweak theory in 1967 was the beginning of the formulation of the modern Standard Model. However, the existence of the Higgs field still had to be determined experimentally, and the predictions of the Higgs mechanism had to hold up. In 2012, the Higgs boson, the excitation of the turned-on scalar component of the Higgs field, predicted by Peter Higgs, was discovered. It appeared that the Higgs field was real. Since 2012, the Higgs boson has stood up to every experimental test. It behaves exactly as theorists predicted the Standard Model Higgs boson should. Given all this, you might be led to believe that the Higgs mechanism we just worked through is the entire story behind how gauge bosons and fundamental fermions acquire their mass. But we're actually a long way from being able to say that definitively. We now understand where the classical Standard Model form of the Higgs potential comes from, and how the changing form of that potential is integral to explaining why the W and Z bosons are massive, despite underlying gauge theories insisting that they should be massless. And we also understand how fundamental fermions acquire mass by pinging off a unique and constantly switched on quantum field. However, there is a massive and gaping hole in our understanding of how fundamental particles acquire their mass. Despite the importance of the Higgs potential in explaining the evolution and current state of our universe, and despite the ubiquity of the infamous classical Standard Model Higgs potential in popular physics media, the true shape of the Higgs potential in our universe has never been experimentally validated. The discovery of the Higgs boson in 2012 verified that a Higgs field exists. It went part way to verifying the Standard Model picture of electroweak symmetry breaking and how fundamental particles acquire mass. However, it gave us very little insight into the shape of the Higgs potential. Just as particle physicists assumed the Higgs boson existed for the more than 50-year span between Higgs's seminal papers and its discovery in 2012 at the Large Hadron Collider, physicists are still assuming that our Standard Model picture of electroweak symmetry breaking is correct and complete. But what if it isn't? The form of the Higgs potential in the Standard Model is the simplest and crudest form that gets the job done. The bare bones form of the potential that ensures that the weak bosons and fundamental fermions are massive in our modern universe. This classical Standard Model Higgs potential was lifted wholesale from the work of Landau and his theories of ferromagnetic phase transitions. It is therefore the potential of a ferromagnet slapped onto the vacuum of our universe. As such, there is no guarantee that it is the correct description of our universe, and frankly, it would be phenomenally serendipitous if it were. The hard truth is that there are many different ways to roll down a potential hill. As such, there are many competing theoretical shapes of the Higgs potential. All these potentials display rings of identical energy ground states. All require the vacuum of our universe to roll down a potential hill in one specific direction and break 3 directions of the Higgs field, and hence facilitate spontaneous symmetry breaking, the production of Goldstone bosons, and the creation of 3 massive weak gauge bosons. And all produce a constantly switched on scalar Higgs field throughout the universe that gives mass to fundamental fermions. All these potentials solve the problems that the Higgs field and Higgs potential are designed to solve, but each is associated with a radically different evolution of our universe and the existence of radically different beyond Standard Model physics and potential answers to some of the biggest open questions in particle physics. This should raise alarm bells and an incredibly pressing question, a question that I will leave you to ponder until our next episode. Which Higgs potential is the true Higgs potential of our universe? You now understand what the Higgs potential is, the form it takes in the Standard Model, the problems that form addresses in particle physics, and that the true form of the Higgs potential in our universe has never been experimentally verified. You understand that our current model of how fundamental particles acquire their mass is a theorist's best estimate and still requires significant experimental verification. Verification that can only be provided by new, more powerful particle colliders. In episode 3 of this series, you will discover why gaining an understanding of the true form of the Higgs potential in our universe and a more complete understanding of how particles acquire their mass is of such paramount importance. See you next time. I want to know what you think, because you're the scholars of enlightenment that I do this for. So please take a moment, if you wish, to let me know down in the comment section. And if you like this video, please consider leaving a like, subscribing, setting up notifications, and sharing this video more widely. I can't tell you how much these simple actions help me out and how much I'd appreciate it. Thanks for watching. Thanks for being scientific. Thanks for being bad.